Bom, boa tarde. A gente está retomando essa série de palestras de apresentação, seminário de apresentação, onde a gente trava um primeiro contato com novos pesquisadores da casa. Hoje vamos ter dois palestrantes. O primeiro deles é o João Pereira, que ingressou no IMPA no ano passado, e vai falar para a gente sobre o método dos momentos. João, por favor.
Obrigado por esta oportunidade para falar a toda a gente. Toda a gente consegue ouvir? Acho que sim. What? Yeah, I'll speak in Portuguese with slides in English. So, eu vou falar em português, os slides vão estar em inglês. Acho.
It's up to you, João.
I can switch to English, yeah. I can do that. Yeah, the slides are already in English, so. Okay, so today I'll be talking about the big project of mine about method of moments, where I think of this in two fronts. One in the front of sample complexity, and the other one in efficient implicit computations. Before I start on that talk, let me tell you a little bit about some of my projects. So one of them is in this tensor works. So you see here, there's nothing about method of moments, which is in the title. We'll get there afterwards. But the idea, I work mostly in three things right now. Actually, there's more things, but these are my main three projects. Tensors, tensor decompositions, and things like this, which will be the main focus of this talk. I also work in the sample complexity of inverse problems, in particular problems that have very high noise. And also I have this work on using machine learning to learn PDEs and STEs. And so today I'll be talking mostly about the first one, with some intuition and a little bit a summary of what I've done in the second one. And then the third one I'm not going to talk about today, but I already gave a talk at Centropy about this. So if you want to learn more about that, you're welcome to check the YouTube video. This was recorded about that third topic. And so what are tensors? That's whenever I tell people here at IMPA, and actually around in a lot of places, when I talk them, I work in tensors, they make a face like, what is tensors? And sometimes they even ask me, what is tensor? And so, okay, first thing is, what is a tensor? The tensor is a multidimensional array. So people in machine learning, they have seen these things before, and even, so it's not very hard to think about. You take a matrix and then you make you can make another dimension, and now you have a 3D table or a 3D array, and that's already a tensor. That's the kind of tensors I'll be working with. And so D is the order of the tensor. And so tensors include scalars, where D is equal to 0, include vectors, where D is equal to 1, and it also includes matrices where D equals to 2. And now if you have D bigger than 2, that's where things start to be interesting, at least for me. And now for this talk, so I'm going to focus on tensors that have the property, they're like cubic tensors. So all the dimensions are the same. And so this sounds a little bit restrictive, but even tensors like this have a lot of applications. And so a tensor of dimension size n, and order d has n to the d entries. And so there's also this, so with tensors, there's a curse of notation, where like if you have more and more more dimension, more orders, you need more indices, right? So a matrix can be indexed by a row and a column, so 2 indices. A tensor has 3 indices for a tensor of order 3. A tensor of order d has d indices, right? And so this is how I index a tensor entry. And the tensors that are I'm going to focus on this talk is going to be symmetric tensors. So tensors that are symmetric are, so a symmetric matrix is a matrix that you can take a matrix and its transpose, and it's the same. The matrix is equal to its transpose. So a tensor is symmetric if it's equal to all its transposes, like transposing all the 6 permutations of the index. And so you can guess that the tensor of order 4 is going to be symmetric if all the 24 permutations of the indices are the same. And okay, tensor symmetric seem highly restrictive, but there's a lot of applications and a lot of places where they arise. So one of the cases is for moments of data, multi-dimensional moments. So what is a moment? So the first one that everyone hears about is the mean of a vector. So take a multi-dimensional random variable. You can take its expectation. This expectation is going to be a vector. And that's the first moment. Second moment, it's going to be a matrix. So the second moment is called the covariance. It's going to capture pairwise correlations between the entries. And so it's pairwise, so you have for each element of the vector on the row and each on the column, you store it in a matrix that you compare all these pairwise rotation, all these pairwise correlations, so you have a matrix. And so we have the first moment, we have the second moment, now we can have the third order moment, which is going to be capturing interactions between triplets of variables. And now that looks like this, and so now we have a tensor. So that's one time where symmetric tensors appear in applications, in data. There's more cases. So the moments I already talked about. They also arise as derivatives of multivariate functions. So the first derivative of a multivariate function is the gradient, so it's a vector. The second derivative is the Hessian, which is a matrix, a symmetric matrix, most of the times, if the derivatives are continuous and everything behaves nicely. And then the third order moment, this third order derivative, assuming the same thing, is also, it's going to be a symmetric tensor. Another application is higher order adjacency matrices. So adjacency matrix is a symmetric matrix for graphs that are undirected. You can construct an adjacency matrix which is 0 if 2 vertices are not connected and 1 otherwise. And it's undirected, so it's symmetric matrix. And then you can do a similar thing for hypergraphs, where you now have triplets of points, and they can be connected or not, and you can form a symmetric tensor with these kinds of connections. And so because of these applications and how these arise in these 3 manners, people have used symmetric tensors and theory and algorithms for symmetric tensors for a lot of purposes and a lot of applications. One of them is Gaussian mixture models. They've also used it to generalize linear models, hidden Markov models, learning neural networks and learning the weights of neural networks, and independent component analysis. A fun fact is that a lot of work in tensors started as an application to independent component analysis and other parametric models. So symmetric tensors really, like the idea of thinking of developing theory and applications for symmetric tensors has really helped all these problems. And so it's really something that can be useful. This talk, I'm going to talk about an application in Gaussian mixture models. But before I go into that part of Gaussian mixture models, let me give you some more explanation about tensor properties that will be useful to explain the method of moments, which is something I haven't explained. I explained moments, I haven't explained the method of moments. And so tensors also have some properties. They are a vector space. They have an inner product. So you can take the inner product of tensors by taking it entry-wise. So what's called for matrices is called the Frobenius inner product. So you have the same thing for tensors. And so as all in inner products, you can define the norm with it. And there's this relation with the norm that everyone knows about, which is the norm of the difference squared is equal to the norm of the first square plus the norm of the second square minus 2 times their dot product. Okay, this is a very simple formula, but we're going to use it later on, so it's good to have it here for future reference. Other thing it's good to talk about already is what's called the tensor outer product. In particular, I'm going to talk about symmetric tensors, so it's going to be symmetric tensor outer product. And so we already know what outer product means for matrices. So if you take a vector and you multiply it by itself on the right, you get a symmetric matrix, a symmetric rank 1 matrix, and that's called the tensor outer product, the matrix vector outer product. And so I'm going to have another notation for it where I'm just going to call it a power in some sense, like itself, a vector times itself, so it's b squared in some squared that is outer product, outer power. Think of it this way. And so we can now think about what we do to go beyond this. So we have a vector, we multiply it like this. Now we can make it 3-dimensional by multiplying on 3 dimensions, doing something like this. And so the ijk entry of this product is going to be bi times bj times bk. Because product is commutative, this is going to be a symmetric tensor. And so we did for 3 order. Now I can't visualize. I can do a visualization for 4th order because we can't do visualization for D unless the people in computer graphics can figure it out. And so we can keep going doing this product D times. And that's the outer product and outer power of tensors. And so with these 2 things defined, so I can revisit the definition of a moment. So the first moment is the expectation of the vector. Second moment is the expectation of this rank 1 product, this outer product. Now the third moment is going to be the expectation of this 3rd order power and so forth for the 5th moment. And so this is the expectation of the higher order moments of a random variable are this. And so what is the method of moments is trying to match the empirical moment with the model moment of a random distribution. So let me explain it better. So suppose you have a model for the data. So let's think, for instance, you have data that looks like a Gaussian. So you say, OK, maybe this is a Gaussian. It has some parameters, like, for instance, the mean and the covariance of the Gaussian. And so you have these parameters, the mean and the covariance. And now you have the points. You want to find the mean and the covariance. So how can you find the mean and the covariance? You can compare the moments of the model with the empirical moments. So the empirical moments is nothing more than the expectation of these, the empirical expectation of these moments. So you take your samples, you take their outer power, and then you average them. So because of the law of large numbers, this empirical moment is going to converge to the actual model moment for the true moment, for the true model parameters. And so what the method of moments consists is to try to minimize the distance between the empirical moment and the model moment. So try to find the parameters that minimize this distance. And so hoping that if you have enough samples, the truth parameters are the true moment is going to be the empirical moment is going to be close to the true moment for the right parameters. So as you minimize this, you're going to be close to the right parameters, to the true sigma, the true theta that corresponds to the model parameters. So here theta, think of it as a vector that contains all parameters. Like for instance, in the example I gave of the Gaussian, it contains the mean and the covariance all in the same vector, and then you're trying to minimize this for all thetas, right? And so you have this minimization of these tensors, which are giant things, and you're trying to find this, right? Okay. That's the method of moments. How did I come to start working on this method of moments? Actually came from a theoretical or this application that involves some application in biology and information theory. So in my PhD, I worked in this problem called cryo-electron microscopy. And so this is a very nice technique in biology that has gotten a lot of attention, especially after getting the Nobel Prize in Chemistry. So in 2017, the Nobel Prize in Chemistry was given to these three people because of the invention and discovery of cryo-electron microscopy. And a reason for this, and so I haven't explained what cryo-EM is. It's a way to determine the 3D structure of molecules. And so one of the reasons that this was really an achievement is because, so in a few years, we improved from having just an idea of what the molecule looks like to a real understanding up to molecules and very nice structure of what molecule looks like. And this is all obtained using this technique called cryo-EM. And so let me explain why this technique is interesting from a mathematical point of view. This is my advisor, which is Amit Singer. He's a mathematician at Princeton. He mostly works on this, which is a very rich mathematical problem. So the cryo-EM problem consists of, so it works like this. So the biologists, their job is to construct, by doing some tricks, to get a lot of copies of the same molecule. So think this helical, I don't remember the name of this molecule, but think, let's call it ribosome. If there's someone that knows biology and knows I'm making a mistake, I'm sorry. So you have, the biologists create a lot of copies of the same molecule, this ribosome. And then after you have a lot of the copies of the same molecule, they put it all in a thin layer, and they freeze it really fast, so that the molecule, the ice doesn't even form things that obstruct the view or anything, and so it's also a thin layer of ice, so you can't have two molecules on top of each other. So you have all this thin layer of ice with molecules in different orientations, and then you take a picture. It's actually an electron ray that goes through it from the top, and it's kind of, you see it on the microscope. And so the data you have is like the molecule in different parts, and it looks like this. So mathematically, the model is like this. You have projections of a molecule over unknown orientations, and you want to reconstruct the original 3D structure. So a little bit more complicated than MRI, because on MRI they tell you to stand still, so they know the different orientations of the slices, right, that they're getting. So it's a little bit like MRI, but you also don't know the rotations. In MRI, you know the different rotations between the model. And so, but also, we're thinking about really small molecules, right? And so that's the part that not knowing the rotation is not the only problem. You also have a lot of noise. And so there's a molecule in there. I don't know if everyone can see it. It's over there. And so it's, the images are really, really noisy. And so that's also a problem. So, but you also have a lot of them. And so this motivated me, and my PhD was working on something like this. So imagine you have a problem where you have a lot of noise, like thinking noise going to infinity, but you also have a lot of samples, thinking samples going to infinity. What's like the sample complexity of that problem? Or, just explaining what sample complexity is, what's the number of photos, molecules, data you need so that you can recover the 3D structure in a statistical sense. And so this sample complexity is a quantity that is known in statistics, and this quantity is it does not depend on the algorithm and estimator you choose, but it depends actually on the statistical model. So think of it as what is the best anyone can do. Nothing, and something like there's nothing that can do better than this. This is related with some ideas in information theory. There's something called the data processing inequality that tells you that if you have some statistical thing and you try to process it, you can get any information, more information. So that thing that people do in CSI, it doesn't actually work in practice. You can't really improve upon can get really information. And using the tools like that, you can really figure out what is like the best error that an estimator can do for a specific statistical model. And so that's going from the error, you can get a sense of what's the number of samples such that the error is less than something, and that number of samples is called the sample complexity. And so this sample complexity can be used to assess the statistical optimality of an algorithm. You can also use it for baseline comparison. You have an algorithm. Okay, I don't know if there's no algorithms out there that do the same thing, but I can compare with the best that any algorithm would do. And now I compute this sample complexity, and I compare what my algorithm doing, the error of my algorithm, against the error that any algorithm would have to do. Like, nothing can beat that algorithm. And this is an average thing, this error, but still, you can see it in practice. And so it also can give you insight on developing new algorithms. And there's an example of that is actually going to come up in the next slide. So what I learned during my PhD was this thing that, so the sample complexity for problems where the noise is very big, like in cryo-EM, is given by sigma to the 2D. So this sigma here is the noise level. So think noise standard deviation. And so what is this D? This D is going to be the order, so the minimal order, such that with moments up to order D, you can recover the parameters of the data. So think of it this way. Suppose you have a Gaussian mixture, a Gaussian model, where you want to recover the mean and the covariance. You don't know this. So you have the data coming in, and now you want to estimate this. You can look at the first moment, but the first moment is only going to give you the mean, right? So it's not enough. You need the second moment, and now with the first and second moment, you have the mean and the covariance. You can estimate the thing. And so the sample complexity in that case, if the noise was very big, would be sigma to the power 4, because D is 2. You can do it with moments of order 2. You can do it with moments of order 1. And so the reason why this happens is because without going much further into the ideas, but so this is going to depend on something called the KL divergence. So the KL divergence, think of it as some kind of distance. It's not really a distance because it's not symmetric, and it also doesn't obey the triangle inequality. But it's bigger than 0, and that's greater or equal than 0, and that's good in most cases. And so this KL divergence is a measure that you have between probability distributions. And when you compare the probability distributions for for different models, so for the distribution but with different parameters, think of like Gaussians with different means and different covariances, you have this quantity. And so the quantity in these problems with a lot of noise, you can tailor it, expand it to have something that is going to depend on the moments. And so this is true for cryo-EM, but afterwards, and in my PhD thesis, we saw this is true for any kind of models where like the noise is very big. Yeah, with some restrictions, of course, but it's very general result. And so here D is the first time where the moments are bigger than 0. Otherwise, so think of it this way. If these moments are 0, you can keep expanding it. The other term 0 out, and then the new term that appears is square of the moments. So that's I call this the domino effect in some way. And so going back now to the, so this was my motivation to start working on this, but then once we had this idea of the sample complexity, I thought, okay, we got the sample complexity, it actually depends on the moment, so let's start developing methods that use the moments. And that's when I started, okay, I'll start developing a method that uses the moments, a method of moments idea to get to work on cryo-EM and problems, similar problems. So this goes back to what I said, that getting the sample complexity can give you an idea of how to develop new algorithms. We got the sample complexity, told us, oh, the moments here are important. So going back to the application, we're going to talk about Gaussian mixture models. So let me motivate a little bit with our Gaussian mixture models. And so suppose you have a lot of data points, right? So this is two-dimensional data points. They can have a lot of dimensions. You can have images that have hundreds or thousands of dimension of 100 or thousands. And so you have these data points, and you want to cluster them, or you want to analyze them. And so what people do a lot of times try to fit a statistical model to it, or create a model, put a probability density that fits these data points, like what I did here. Okay, and so one model that people like to put a lot in data, which the first one that appears in a lot of cases, is the Gaussian model, Gaussian distribution. And so the Gaussian distribution is of a n-dimensional random variable is given by a mean, or also called the center sometimes, which is a vector in Rn. Covariance matrix is Rn by n, and is symmetric positive definite. And this is the PDF, the probability distribution function. It looks like this for 2 dimensions, the PDF. It looks like this from above. And it has a lot of properties that people know about. Like if you sum a bunch of independent random variables, it's going to converge to a Gaussian. It's symmetric around the mean, and the marginals are normal. Conditional distributions to conditional on other variables are normal, et cetera, et cetera. So they have really nice properties. And so, but if we go back to the example I had before and you try to fit it a Gaussian, it's not going to work. Like, you definitely have 3 clusters on there, and the Gaussian is not capturing that. So can we come up with something that has clusters, kind of clusters the data, and has a Gaussian thing on it or something else? Okay, there's something called the Gaussian mixture model. So it's a mixture of Gaussians. So think of it as so the PDF is just the linear combination of the PDFs of a Gaussian, where the linear coefficients are these lambda j's, which live on a simplex. So they sum to 1, and they're greater or equal than 0. And so this is what the Gaussian mixture model looks like with 3 terms. You can do it with higher dimensions as well. And so if we fit the Gaussian mixture model to original data, it looks much better. Yeah. Disclaimer, the data actually comes from a Gaussian mixture model, so it makes sense that it looks much better. even the Gaussian mixture models itself, which was already an application, people use it with symmetric tensors, even the Gaussian mixture models themselves have a lot of applications. So one set of applications is just trying to estimate the density that can have applications like you want to model prices of things, like think of modeling the price of houses in a city. Different places of the city have different average prices, and you can model this with a Gaussian mixture model. You can think of topics in a document where things also cluster, so you can also model this with Gaussian mixture models. You can use it for clustering, so you can use it for image segmentation and point set registration. So the idea about point set registration is that if you have a cloud of points and you kind of want to compare them and see if one corresponds to the other after a rotation or something, what you can do is if they can take these two clouds of points and approximate them by a Gaussian, and now you just compare the two Gaussians and try to figure out what is the correspondence. And you can also use it for anomaly detection, because once you have a model for the data and another thing comes in, you can say, OK, this thing is very unlikely. It has a very low probability, so it's an anomaly. And it's a way you can use it for anomaly detection. And people use this for handwriting recognition, financial models, and also to detect fraud and things like this. And so one small thing before I go further is that we're going to focus a lot on real-world data. So I gave an example with thousands of points, two-dimensional points, but in practice, things are many more data points. Think 10,000, 100,000, even millions sometimes. They also have much higher dimension. Like images are very high dimensional, and things in general are like data points can be very high dimension. So we'll be thinking about data that has this kind of number of points and dimensions. And so let's start and try to, so we're thinking about method of moments. So let's talk about what are the moments of Gaussians and Gaussian mixture models. So before I go to the formulas, let me define more things. So I defined the outer product, the symmetric outer product. But you can do all kinds of products. You can do products with different vectors. You can do a vector times a matrix, and I have an illustration there of how it works. And we can do a vector square times a matrix, matrix times matrix, you name it. But there's a problem with doing all of this, is that so the vector to the power of something is going to be symmetric, but in general, depending if the matrices are different, these other products that I defined are not symmetric. And so we're thinking about symmetric tensors. So is there a way to go from a tensor that is symmetric, that is not symmetric, to a symmetric tensor? There is. It's a simple one. You take a tensor, and then you take the average over doing all permutations of the indices. OK, and so this is an example with the b times c, and you have all these permutations, and now you have a symmetric tensor. And so with this symmetrization, the formula for the tensors for the moments of Gaussians gets much easier to explain. So the moment of a Gaussian, the first one is the mean, is the center, right? And the second one, I think a lot of people also know it here. It's the mu transpose times sigma, mu transpose plus sigma, where so mu is the center of the data, and sigma is the covariance. And then what a lot of people do is take the mu transpose part, which is thinking about as the centered moment, which gives you the covariance sigma. OK, so what is the third order moment? OK, it's going to look like a tensor, but the formula, like I've seen the formula written where like you think about it as like mu times sigma plus mu times sigma on the other direction plus other things. And so there's a much easier way to write it, which is the symmetrization operator. And it looks like this. And the fourth moment looks like this, and you can keep going, and you get this formula for the moment of Gaussian. So this is a new result, but kind of not everything new. So the moments of Gaussians are known, but the formulas that were available before were like you have an element, you have to take the symmetrization over that element of something that looks like that product, which it didn't look that nice to deal with, the formulas. In particularly computationally, like you'd have to symmetrize this for all elements. It was not really easy to see this formula. And so that's something new, like having a formula that is also easy to calculate and can be used in practice. And an interesting thing is that the term that appears is the 2kth moment of a univariate Gaussian. And so it generalizes the moment of a univariate Gaussian. It makes sense, right? And so it's related to, actually the proof ends up being reducing the higher order moment to the moment of a Gaussian. But I don't have a lot of time to go into the proof of this, and just say that if you have a Gaussian mixture model, okay, so if you have a Gaussian mixture model, the moments is just the linear combinations of each of each of the distributions that you have in the mixture. So it's just a linear combination of lambda j times the nj's. And this is the formula for the moment. And so we already have the moment, a formula for the moment order. So what we could do already would be optimize using this formula. So we have the empirical moment on one side. We have this model moment on the other side, so we could do that, like I explained here. But there's a problem. So now the curse of dimensionality comes in, right? So think about it. You have a vector. Okay, a vector is fine. Think of it as samples in 500 in dimension 500, and you have a lot of them. And so, okay, a vector of dimension 500, that's okay. A matrix 500 by 500, okay, that's already kind of big for a computer, but it can do it easily. But now a tensor 500 times 500 times 500, computer is going to take a hard time on that. Even if you take it to order 4, then forget it. It's going to take a long time. And so doing this optimization would be very costly, right? And so we could kind of lose hope to do something nice. There's a lot of work done for one-dimensional random variables and the method of moments, but people lost hope with these higher order moments. But now we have something, a simple idea, but can be quite useful, which is, so how can we calculate this without really forming this tensor moment? So we have the formula for this, but we're actually going to try to calculate this without forming the moments. And so before I go into explaining this, there's this really nice property of the inner product that I defined before, is that, so if you have A to the power of 3, so this outer product, A outer product 3, and B outer product 3, so you can see by this little argument that if you have their inner product, you can separate the sums, and it's just going to be the inner product of A and B times the inner product of A and B, so the inner product of A and B cubed. So the nice thing about this formula is that on the left side, we have something to use things that we're calculating the inner product, but on the right side, we have something that is very easy to calculate. It's just you take the inner product of the vectors and you take it to the power of 3. So in general, this is also true for higher order tensors. And so we're going to use this. And, but there's more things that are true. So if you have a tensor of order G times some products of tensors, things are also nice. And so we're going to use this. So why is this going to be useful? Because the empirical moment is just a sum of terms like this, right? A sum of rank 1 elements. And so if we take this inner product and now expand it using the formula that I gave in the beginning, so it's the norm of the first plus the norm of the second minus 2 times their inner product. And now the first term doesn't depend on sigma, which is one we're minimizing. So in other terms, this first term doesn't depend on the parameters of the data. And so we can forget about it. And so there's two terms that we really have to care about. One is the inner product between the elements, the samples to the power of d, and these are their moments. And the other term is these cross terms with the moments of the Gaussians for different centers. So how can we calculate this? For the first one, I'm going to take back the formula of the moment, and I'm going to give an example calculation. And so we can take this third order moment. We can calculate the dot product between xi and mu j to the cubed like this. We can also use the same thing. I used here something interesting, which is this symmetrizing operator that I talk about on tensors. It's a self-adjoint operator. It's actually a projection operator. And so I took the symmetrization on the right side. I put it on the left. And so the xi cubed is a symmetric tensor. And so it just disappears, the symmetrization. And so I have something which I gave a formula to calculate already. And this is the formula for it. And so the good thing about this is that for a fixed xi, a fixed mj, the only things I need to calculate, and this is true for d equals 3, but also for higher order d, is the inner product between xi and mu j, and this inner product between xi and sigma j, which is written in this way. It's like xi transpose times sigma j times xi. And so that's the two things I need to calculate, and then I can calculate all dth order inner product. And so there's also the other term. The other term is a little bit more tricky. So it's the dot product of two moments. But then we can use a cool trick of probability and expectation. So we can take the expectation of the vectors. So the formula is given by this. And then on the second line, we use that the expectation is linear, and now if the xi and xj are independent, you can bring all the expectation outside and do this formula like this. And now the good thing about doing this outside, so I basically took the expectation and put them all outside, using that the inner product is bilinear, right? Linear on the first term, linear on the second. And now using this, now the part on the inside will use the same formula used before, and it just becomes a dth moment of a univariate variable. That depends on the distribution of xi and xj. But we can, so what we did is we took this univariate random variable and we calculated its cumulants. We have a formula for them. And then from the cumulants, we go to the moments using what's called Bell polynomials. There's a formula that relates the cumulants with the moments, and it's called, it involves Bell polynomials. And so we have a formula for calculating all of this. And so in the end, we get something that, so instead of building these giant tensors, and that would not even be able to be done in a computer, we just calculate these things using these kind of ideas. And so we overcome what's called the curse of dimensionality, where, so the curse of dimensionality would be building these very big tensors. We don't need to do that. We can do everything without building all these big tensors. And so to calculate the function values and the gradients, we have these costs, which don't scale exponentially on d anymore. Actually, they don't scale on d almost nothing. There's a scaling on d somewhere in there that I forgot, but it's linear, or at most it's quadratic on d. And so it's it's not as bad as it would be forming the tensors. And I told you about calculated function values. You can also calculate the gradients. And there's something here for people that are used to this. So I was thinking about the moments, the empirical moments. But what you can do is you just select some samples, and then consider just those few samples as your empirical moment. but now you do a stochastic gradient. So this is called what's called the stochastic gradient when you just select some of the samples and then you run with these fewer samples. But you also put some moment on the gradient. So the idea of selecting fewer samples is that you can do this faster, and if you put some moment on it, it's still going to converge to the real thing. So the idea is that everything I've done so far can also be done with stochastic gradients and function values. And so now let's go to see how this works in practice, and I'm going to compare with EM. So expectation maximization is the algorithm most people use for Gaussian mixture models. Actually, I feel like it's the only algorithm people use for Gaussian mixture models. And there's nothing else people do in practice, and so it's a great algorithm. It works nicely. So it works by first you compute these memberships for each of the centers, and then you update the component parameters using those memberships. It's like a two-step optimization. You minimize this, and then you minimize that. And then by doing these two steps, you're always guaranteeing that the likelihood that the likelihood of the samples given some parameter is increasing. So the likelihood is increasing. The parameters the likelihood that you're choosing the right parameters is increasing, and but it can get stuck, and it has some problems. So these are the good things, but then they have some problems. They are sensitive to initialization, and so they're not guaranteed to converge, so they can get stuck in local minima, and so you have to repeat a lot of times. And there's also this problem where, like, if you have two Gaussians close together, it tends to not work well. And so this goes to explain. So this is a great method. This is a great algorithm, but it's the only one. And then people use it, and they're like, OK, this is not working well. I need something else. And so what we propose is try this algorithm that we just came up with, the method of moments, if that happens. And so on the other hand, method of moment has some theoretical advantages. People have studied it a lot. And we compared our method with the method of moments with EM, and we saw that it did very well. So in this case, so the parameters that we chose are on the left. In this case, even using the method of moments gets us already higher likelihood. So let's think we are optimizing a different function, and they're still getting better on their function. It's better on our objective. It's a little bit slower, but it's better in recovering mu, sigma, and sigma, the parameters of and lambda, the parameters of the Gaussian mixture model. Another example here, now the EM was better in their own objective, but we were still better in most of the other things that we were measuring. We were better in recover lambda, mu, and sigma. And so to wrap up, I talked about two things. One was the sample complexity of these very high, very noisy or low signal-to-noise ratio problems. And we saw that the sample complexity was given by the moments of the data. And the other thing was getting this formula, this nice amenable formula for Gaussian mixture models. And we also got to this efficient computational and storage algorithm that makes this optimization easy and comparable to do with EM. And there's some things for future, but I'm going to speed through them because I have 2 minutes, so I can talk a little bit about them. One is improving the implementation details. So this was the paper itself. We have to talk a little bit more about what we do for general Gaussians. The formulas are there, but the implementation details could be improved. for a mathematician point of view, this is like, okay, the formulas are there, it's done. For some people in practice, it's not like that, but the formulas are there. So, analyze the optimization landscape. So, what we notice is that EM was getting stuck more often than the method of moments. So they're optimizing two different problems, and the EM was getting stuck more often than the method of moments. And so we think, is there something going on there? Is the optimization landscape for the method of moments better? We also want to study the sample complexity of this problem, and in particular, compare, see what's the number of samples that our algorithm needs to get to estimate the parameters up to some error, comparing it with the sample complexity that any algorithm can do. And apply these in different data. So we use mostly synthetic data, but it would be nice to have real data to apply these to. And I'm already working on things like this. And then also apply this for all other distributions, other applications, using this idea of the implicit method. So work with moments without forming them. And that's it. I have an extra, but I'm on time. So if there's no questions, I can go to the extra. But otherwise, that's it.
Are there questions?
So, can you hear me?
Yes.
So, you focused a lot on the complexity. What about the regularization? Since probably you have a very impulse problem. So, does the method of moments work well for regularizing the problem, like information a priori and so on?
Okay. So you asked if this works well for regularization. Are you asking like make it more robust to the data? For instance, like the first and second order moment are good, give you like some other methods are good, but they're kind of finicky with the data. But with higher order moments, you get more information that you can use with the data. You can also use different weights for the orders that you use. And so consider higher order, but then for moments of higher order, put a lower weight. I think this can be quite useful for regularization, I think.
I'm talking about incorporating regularization in the algorithm, like trying to use a priori information.
So this is good with that. Like this optimization algorithm, right? So in the end, it was optimization. So if you have restrictions for the parameters, you can put that in the optimization, and that will work fine. It also optimizes for the models of Gaussian, right? So you're stuck to being a Gaussian with different parameters, but still a mixture of Gaussian. So in that way, that also regularizes what you get in the end a little bit.
Any further question? If anyone wants to make a question in Portuguese, is also more than welcome.
Yeah, eu falo português também.
If that's not the case, so let's thank João again.